Good morning. Good morning. I have the honor of being the hype man for the Innovative Research Award of Excellence this morning. The Innovative Research Award of Excellence recognizes individuals who have made outstanding contributions to the area of research in the world of digital design and computation. This year we are honored to have Andy Payne receive this award. Andy is not only an example of an individual who has made significant and powerful contributions to the world of computation, but someone that is an example of an individual who provides a collaborative spirit and an optimistic outlook on this world that we inhabit and are so passionate about. I could cover the whole spectrum of the things that Andy has done, but I'm going to let him do that. I'm going to highlight 3 examples of why we selected him as a group. I think very few, if any of us, have not benefited in some way from Andy's contributions, ranging from the Grasshopper primer that was created so many years ago, which I would credit as accelerating the adoption of computational tools like Grasshopper into our practice. I can't count the number of times when I was working as a designer and I'd walk into another practice or talk to some other colleagues, and they would have printed out this very large document authored by Andy. His collaboration with Jason Kelly Johnson on Firefly introduced the Grasshopper community to the idea of bridging between the digital and the physical. And not only that, but I would credit that plugin as one of those early contributions to the community that has kind of unleashed a torrent of plugins and contributions from others. It really set the stage for this culture of sharing that I think we in the KDA community and in the computational design community are so proud of. And then finally, his latest work at Autodesk as a researcher and his work with Monolith to really push the boundaries of how we work with new modeling paradigms and how those new modeling paradigms are contributing to a new way of making. I had the pleasure of working with Andy when I was a director at Case. I could sing his praises as a collaborator for a very extensively. He was an amazing person to work with. I couldn't speak more highly of an individual that brings both intelligence, rigor, and he's just an all-around nice guy. And I know that he's got an amazing presentation, so I want to cut to the chase here. Ladies and gentlemen, Andy Payne.
Thanks, Nate, for that introduction, and of course, thank you to the Acadia community for this award. It's really an honor to receive the Innovative Research Award of Excellence and share the stage with such an accomplished group of award recipients. You know, a lot of my work has been supported over the years by so many different people, many of who are here in the audience, and I would simply just like to say thank you for the generosity of time, the inspiration, and just your overall support over the last number of years through my research. So I'll see if I can switch over. Okay. So I've titled my talk today Identity Crisis, primarily because I find it increasingly difficult to describe to other people exactly what it is that I do. So we'll see how this presentation goes. But I also think that we're at a bit of a crossroads because we're starting to see the true definition of architecture beginning to change. Like many of you, I was trained as an architect, where we, went to school and learned how to draw and had some courses in history and theory. But what we're starting to see in education today, and I think this was echoed with Thea's presentation yesterday, which was really amazing and inspiring, was that we're starting to see many of these different disciplines beginning to challenge what that definition is of what it means to be an architect. We're seeing so many different fields and domains that we're asking students to begin to master. That's really, I think, changing the discourse in many ways. But that's not necessarily revelation, because architecture has always been seen a bit as a universal type of education. What I find compelling is that technology is really beginning to blur the distinctions between these different domains. But even more so, we're starting to see that form new trajectories of how we begin to communicate and bridge these different disciplines. I found that a sort of a theme that runs through my work is that I've really strived to form new workflows and new processes to bridge many of these different disciplines. And of course, one of the first projects that I had the opportunity to collaborate on was this project called Firefly, which I started back in 2008, 2009 with Jason Kelly Johnson. And as Nate alluded to, Firefly is sort of this bridge between the physical and the digital worlds. It is a plugin, of course, for Grasshopper, but I think what is powerful is that it allows us to take real-time information from the world around us, to sense anything we want to sense in the world around us, and use that as a driver for three-dimensional geometry. So we can have, here you're seeing a light sensor, but we can have any number of sensor inputs driving real world or digital prototypes, or conversely, we can have parametric data drive our physical prototypes. So we can no longer just leave it in the domain of the computer with our designs. We can actually begin to feed that out and drive, real world interactive prototypes. But we also have the ability to, use maybe more unconventional methods of sensing and actuation. So here, I'm actually blowing on the microphone of my iPhone and sending a wireless signal over to Grasshopper to simulate a wind vector in the computer. But so we can actually use many different types of devices, such as iPhones and game controllers and webcams, or even the Microsoft Kinect to basically track your position within an environment and then map that to a control strategy. In this case, simply increasing the brightness of an LED or controlling the position of a motor. These are quite trivial demonstrations, and most took only a couple minutes to put together. But what I find interesting or compelling about Firefly is that it really takes challenges our ideas of what a feedback loop can be, where we have a sensor and an actuator and some sort of predefined behavior, and then begins to hybridize that into something maybe more of an interactive feedback loop, where we can actually take our sensors and drive digital geometry or parameters to drive actuation, or really any combination within that workflow. So those were relatively simple, trivial demonstrations, but one that's a little bit more intricate was a design, and again, I think this speaks to this idea of sort of creating a new workflow, but that I developed to enable robotic fabrication for designers, particularly that may or may not actually have the design to fabrication knowledge to actually run robots, industrial robots. The reason I sort of set out to work on this project was because the design to fabrication workflow for industrial robots has, traditionally been a really slow and cumbersome process, particularly for designers. Machine tooling, there's kinematic simulations and robotic movement programming, often require an intimate knowledge of scripting and manufacturing processes, all of which sort of limit the utilization of these tools by, say, your typical architect and designer. We have a fabrication workflow where a designer often has to hand off their design to a fabrication consultant who has, more intimate knowledge of these different processes. And if there's any irregularities or singularities or errors found during that process, we have to feed that back or hand the digital information back to the designer, who then has to edit the design, and it's just a very slow and cumbersome process. So I set out to actually create a more intuitive interface, say a physical, tangible interface, to go directly from physical input to direct robotic fabrication. So I designed a tangible controller that is built off of the same axis and joint configurations as the 6-axis industrial robot that we had at the Graduate School of Design. So those blue knobs there in the middle are high precision potentiometers, which essentially just measure the angle of rotation. So if you know the angle of rotation and you know the length of each arm, then you can perform a real-time forward kinematic simulation in the computer. So here you're seeing just a real-time demonstration of moving the tangible controller and seeing a real-time simulation of the ABB robot. And of course, if you can perform the forward kinematic simulation and you know where the end of the tool is, then you can certainly start to create real-time robotic tool paths and record that information. So recording that information, you can write that information out directly to Rapid Code and send it to the computer, or we took it a step further and actually began to stream this information directly to the robot itself. So here you're seeing a direct workflow going from the physical interface through Firefly and the sensors, and then performing this simulation and streaming the data directly to the robot. So again, this is a bit of an older project back in 2011. This was presented at Acadia, but I think it begins to speak to how we can begin to use these embedded sensors and the world around us to hopefully create more intuitive interfaces and a more streamlined approach for robotic fabrication. Now, my work with Firefly in particular, and the idea of embedding sensors in the world around us, and also beginning to explore how we begin to map those into intelligent behaviors, really compelled me to ask the question which sort of led to my doctoral research, which was, what does it actually mean for architecture to be smart? You know, I think this question was raised again in Theo's amazing talk yesterday. We hear all the time these smart cities, smart buildings, smart environments, and smart products, and I think if we polled the audience today what their opinion is on smart architecture, you would get 300 different responses, because there's really no universal definition or no universally accepted definition of what it means for architecture to be smart. Now, of course, if you did a review of the literature, what you would find is that the evolution of smart buildings has really revolved around the integration of various building control systems. So starting in the 80s, where we had completely single-function, isolated building systems, to today's systems that are completely cloud-based and not only networked within a building, but have complete networks between buildings. But I think that the control strategy, the how and the why things begin to get turned on and off or controlled, is still largely based on a very antiquated, reactive, or automated model of control, where we have a sensor in the space and it's mapped directly to some sort of actuation which has been predefined by the system architect or the system designer. I think that brings up a question: is what is the distinction between smartness and intelligence? Right? Intelligence, I think, underscores the capacity for learning and reasoning and understanding. And I would argue that I think architecture needs to move beyond this realm of smartness into the realm of intelligence, where our buildings and our spaces have the ability to learn how they're being used by the occupants and begin to adapt accordingly. So this was really the domain that I was exploring in my doctoral research. And I was specifically looking at thermal comfort. Because it's been shown in many different studies that thermal comfort is one of the, if not the primary driver of dissatisfaction, particularly within office environments. So in order to describe a little bit of my research in more detail, I thought it would be prudent to at least describe how our buildings are designed currently for thermal comfort. And much of it actually comes from the research that was done by P.O. Fenger in the late 70s and early 80s, where a large number of physical climate control tests were done and conducted, and he basically was able to boil down a model that was based on 6 primary factors. There were 4 environmental factors like air temperature and radiant temperature and airspeed and relative humidity, and 2 personal factors such as how much clothing a person is wearing and what type of work they're doing. So those 6 factors basically go into a large equation that he derived and spit out a number between -3 and +3, which tells you the environment. Basically, it's called the predicted mean vote, where a -3 would indicate that the environment's very cold and a +3 is the environment's very hot. So of course, if you know that number, he was able to extrapolate from that the percentage of people who would be dissatisfied in that environment. So I set out to design an interface that could harness machine learning algorithms. In particular, I was looking at neural networks. So I designed a neural network training interface that could take the work of Ole Fenger's predicted mean vote model, which has these input values that are these 6 parameters, and return the predicted mean vote, this number between -3 and +3. So the interesting thing about neural networks is that they have the ability to adapt over time based on new evidence or new feedback given to the system by a user. So in this case, I can train the neural network to approximate the ASHRAE standard of this predicted mean vote. But as I begin to propagate new feedback, so if a person says, the environment says that it thinks you should be warm, but in reality you actually are cold in this environment, you can indicate to the system that you are cold, and it will propagate or retrain the system and adapt accordingly. So I think the way our systems are designed right now is based on this average user. This predicted mean vote is based on the average user. But I know that if you're like me, that everybody has a very different opinion as to what that means for thermal comfort. And so I think we need to begin to harness new techniques using, say, machine learning or artificial intelligence to have our systems begin to adapt to us based on new feedback. So I know I didn't actually get into the details of what you were actually looking at, but really the essence here is that in the center you can see an overlaid model where the fit of the neural network output versus what the actual equation gives you is quite close. But as you begin to propagate feedback, you can actually create a model that shifts towards the cold domain or the warmer domain. So the software was really only one part of the problem that you have to solve. The other side of this is hardware design. So I set out to design a number of different hardware devices, including a low-power wireless sensor module that could track temperature and humidity and light levels and occupancy detection. I also designed and built a AC power adapter that could wirelessly turn on and off anything that you plug into it, like a task light or a personal heater. And also we need our devices like our desk fans and our task lights to be able to communicate back to, say, a central system. So I also created a HVAC remote control that could wirelessly talk to our central building systems and turn on and off and control the HVAC system. But I think one of the more intricate hardware devices that I had the opportunity to design and work on was this personal desk fan, this sort of smart desk fan. And I set out to design this desk fan because I found a study that showed that you can save 17 to 48% of your cooling cost if you simply use a low power fan to offset the thermal impact of increasing the ambient temperature in the room just a few degrees. Now, there's 12 billion square feet of office space in the US, and we, on average, use about 2.42 kilowatt hours per square foot. Now, if we were to assume just a very simple, or take the national average of cooling cost per square foot of 10 cents, we spend on average $3.1 billion every year cooling our office environments. Okay, so what we're talking about here is just using a simple idea of a low power fan, but have the opportunity to save over potentially $1.5 billion every year. So it has a large financial impact, but also has the ability to impact productivity and, of course, occupant satisfaction. So I set out and I designed a low power fan. A typical desk fan is about 20 watts, and this is a 6-watt fan, so using two 3-watt fans. But it also has an embedded webcam in the bottom because it's been shown that you can also save energy if you focus the cooling directly where it's needed most, which in this case is your face and neck region. So it uses facial recognition algorithms to actually move the fans and direct the cooled air exactly where it's needed. So in order to actually show it off, I just figured I would show the video instead of talking more.
Meet the new Smart Fan. This little guy is designed to be the smartest smart fan ever invented. He has the ability to learn when and where to focus his attention, using facial recognition to direct cool air towards parts of the body that most affect comfort, like your face and neck. He's also smart when it comes to energy. Studies show that we can save a substantial amount of energy if we raise the ambient temperature in a room just a few degrees and use a low-power fan to cool off the body. Yet most fans only have the ability to perform one of two actions. They can either sit still or oscillate back and forth. Because most people don't sit still or rock back and forth all day, regular fans waste an inordinate amount of time and energy cooling the area around the actual person. Needless to say, that just blows. The Smart Fan uses two small 3-watt fans, drawing about a third of the power of a typical desk fan. Plus, with his built-in video camera and facial recognition software, he spends all of his time and energy making sure you feel good. The Smart Fan also has the ability to communicate with everyday devices like task lights, personal heaters, and larger building control systems. And as if that weren't enough, he also uses state-of-the-art machine learning algorithms to get better and better at maximizing your comfort. Smart, right? Welcome to the future of personalized comfort control. Your personal desk fan just got a whole lot smarter.
All right, so again, software, hardware, that was part of the equation, and unfortunately because of the brevity of this talk, I don't have the ability to go into more detail, and so I'd love to talk more about it if you're interested. But what I would like to do sort of is switch gears a little bit and talk more about some of the research I've been doing over the last couple years with a colleague of mine, Panagiotis Michelatos, where we had the opportunity to begin to explore new methods of additive manufacturing, particularly with multi-material 3D printing, which allows you to deposit, different types of materials throughout a volume. But what we found quite early on was that the way we represent geometry in the computer is still quite limiting based off these new additive manufacturing processes. And that's because I would say 99%, if not all of the CAD software out there are built on this idea of a boundary representation, where we as architects are actually trained to design objects as a formal investigation, but everything inside of those objects are actually treated as a solid homogeneous piece of material. And I think this largely stems from an extension of the Industrial Revolution, which sort of taught us about this assembly paradigm. But we're starting to see other disciplines, particularly the biomedical industry, which is pushing different ways of thinking about representing material throughout a volume, like, say, an MRI scan, which treats density of material and can control that and begin to scan that information and do 3D reconstructions. So some of the work that we're looking at is how do we form new representations or hybrid representations where we can build off of this idea of volumetric modeling. And it's largely built off this idea of a voxel, which is simply an extension of a pixel. It's a volumetric pixel. And just like a pixel, which is just an array that has information stored, say about the color, the red, green, and blue of a certain position in space, the same is true with a voxel. You can store any number of channels of information about a three-dimensional location in space. And like a pixel, we can actually begin to extend many of the same operations that we do in 2D, but now into the third dimension. So what we've been working on is a project called Monolith, which really begins to explore, and I will be the first to admit that we still haven't nailed it, but explore from a user interface perspective how we begin to make, say, a hybrid modeling environment where we take the elements of traditional CAD that we're used to, points, lines, curves, and surfaces, and marry that with, say, three-dimensional image editing techniques, raster editing, and then also adding in elements of parametric design. So it's quite a challenge, but also something that I think opens up some really interesting creative possibilities, like 3D painting within a three-dimensional space, but then having the ability to use filters that were common in 2D image editing, say like a Gaussian blur, but now you're performing a Gaussian blur on a three-dimensional model. Also, because we have physical locations in space for each voxel, we can multiply those by, say, a known formula and create different mathematical surfaces, or create sliders on the fly, which allow us to look at a larger design space quite quickly. And because a voxel is also very similar in nature to a pixel, we have the ability to basically use images, two-dimensional images, and new techniques for blending images. So again, if you were to try to model this with an existing boundary representation model, it would be quite difficult, but we have the ability to perform very complex topological operations very quickly by being able to blend seamlessly between these different ideas. We also have the ability to take in existing geometry from other CAD programs. So we can read in meshes and begin to operate not just on the surface, the way most CAD models would work, but also on the interior of that object. Or also using other representations that, again, are more common to the way we're used to designing, so points and lines and curves and surfaces, but now we have the ability to smoothly blend the geometric representations. And this is just a few different videos showing how we can do different operations, largely at a macroscopic scale, of how we can begin to push and pull and interpolate a three-dimensional space differently, just the way you would do in an image interpolation, but now you're doing it in three-dimensional space to control geometry. So that's one side. One of the benefits of a voxel-based modeling engine is it gives you these really interesting ways of operating. But I think what we're starting to see, as I mentioned, is the hardware is starting to push us in new directions as well. And it's forcing designers to begin to question what it means to question materiality, and what the scale that the architects begin to work at. So we can really start to get down to a single drop of resin, and what does that mean for an architect? So we're also looking at different half-toning techniques, three-dimensional half-toning techniques, which allow us to propagate micro patterns, if you will, throughout a volume. And those obviously have different optical as well as elastic and structural properties to them. So here you can see just applying different UV-W mapping parameters. So again, different from just the U and V, we now have the W parameter that we can go into the volume of the space. So we can quickly actually explore a wide variety of micropatterns and how those might begin to behave. But it also allows us to then create really interesting patterns that have, as I mentioned, elastic properties, and create anisotropic material distributions where we can control the bending of an object exactly where we want it, or say have view-dependent optical occlusion, so we can begin to reveal things within a volume based on where someone is viewing that. Now, voxel-based modeling also has the opportunity that it simplifies in some methods some different analysis techniques, including, say, a structural analysis technique called topology optimization. So Monolith has a topology optimization module inside, which allows you to essentially define a loading and boundary condition, and it will it will distribute the material within a volume to optimize for that particular loading condition. So here you're seeing basically a cantilever load on one side and a fixed support on the other, and it finds, say, a truss, and then you can look at the principal stress curves and export those as curves. So we have the ability now, though, what I find compelling here is that we have the ability to create really interesting and complex structural forms, or at least reinforce our ideas. So here you're just seeing a truss that was form found, but it's a little bit different because we can now realize those. We can, in the 3D printer, the clear material in the middle is actually a clear transparent rubber, and the more dense material is a hard plastic. So we have this smooth continual gradient between those materials, which actually lessens the stress concentrations at a typical joint, which is what you would see in a truss. Or we can perform more complicated stress or design operations, in this case using a cantilever load. And what Form finds is a venation type system, because this is the same type of operation that a leaf has to solve for, right? And so you get a very similar venation structural pattern that emerges. And then lastly, I think voxel-based modeling opens up some new opportunities that are currently unable to do with traditional mesh operations. In this case, we're printing hairline features where the lines that you're seeing are the principal stress curvature, but they are only a single drop of resin thick on the print bed. So this would be incredibly difficult to do using traditional techniques, but now we have the ability to visualize and materialize these ideas. So I'm hoping that this talk today showed a little bit about how my work is starting to span a lot of these different topics. And of course, I would be remiss if I didn't thank all of the key collaborators that I've worked with over the years, and of course the industry partners. So thank you for your time.